Hi, everybody. Welcome. I'm Rina. I'm the leader of today's free GRE prep hour. I'm going to give folks one more minute to arrive. I know sometimes it can take a moment to join a Zoom link. So in the meantime, go ahead and introduce yourself in the chat. I see folks already introducing themselves with your name, where you're joining us from, what you hope to study in school. So hi, Phil. Hi, John. Welcome, everybody. And again, we'll start in a moment. Hi, Harold. Hi, Ika. I remember you from the past. Great to see you again. If there's other folks that I also met in the past, great to see you too. Hey, Lauren. Welcome, everybody. All right, so it's 1 minute past the hour, so let's dive in. But if you haven't yet shared with us where you're coming from, go ahead and do so. So as I said, I am, oh, great, awesome, Ika. I'm Rina, I'm an instructor here with Manhattan Prep. I've taught with us for many, many years, and I'm really excited to lead us through tonight's session. Tonight is going to be a quantitative section. We're going to be focusing on geometry and quantitative comparisons, and that's a specific question type that you find on the GRE. Now, I'm going to tell you guys that tonight's session, because geometry has so many rules on it, I am going to operate assuming that you know some of these rules. So if you're like, I haven't studied it all yet, and I haven't learned those triangle rules in a really long time, this will be a great session for you to come back to later. And all of our sessions are recorded. We're recording right now, they're recorded, and they're on our YouTube channel. So tonight's session is oriented more, it's like, how do we apply it to quantitative comparison? But some of the rules I'm not going to spend a lot of time going over the geometry rules, because I want to think about applying them. So, but what I'm going to do, I was going to send you guys a link, but you know what? I don't quite see how to send a link in this particular one, but I think so. I'm going to find another thing to send you guys in a moment. So, okay, let's dive in. I'll figure out the other thing I was going to do in a minute, but here we are. So welcome. As I said, we're going to be focusing on geometry and QC, thinking about applying our geometry rules to this specific question type of quantitative comparison. A lot of our questions today are coming from this 5-pound book. This is a book of a bajillion, approximately, by which I mean 1,000, thousands of practice problems that you can also get online, but that is the source of most of our problems tonight. We're going to do an overview of the quantitative comparison question type, which I've abbreviated here as QC. So we're going to do an overview of this question type. I'm not assuming that you guys have seen this question type before, so I'm going to give us a little intro to this question type. Then we're going to talk about these different strategies for this question type as it relates to geometry. And those strategies are going to be B as a benchmark, and we'll see what that means, proving D, and we'll see what that means too, and a secret common ground. And then we'll wrap up at the end. So to begin, I want to do that quantitative comparison overview. And I'm going to give you guys 2 problems that aren't geometry based, but just to illustrate this quantitative comparison type. And these are 2 prompts that I got from the ETS website. So ETS are the makers of the GRE, and these are 2 sample problems that they've provided for free that give a good illustration of what this question type is all about. So here's the first one. I'm going to put my timer here on this side. 1 minute, and chat to me. So chat just to the panelists your answer when you have it. 1 minute, go for it. All right, thanks for sending me your answers. I'm seeing lots of great answers come in. So this question is a great example of our general idea of proving D for these questions. So our answers here below, A is greater, B is greater, A equals B, they have this always in them. And proving D can mean testing cases is one way to do it, but it's finding examples that break the always, that's there in A, B, and C. So here, maybe I want to test some numbers, right? So I could say like Lionel is 1 and Maria is 2. In this case, twice Lionel's age, so A would be 2, and Maria, okay, she's still 2, right? So Maria would be 2. In this case, our two values are equal. But what if Lionel is still 1, but Maria, his big sister, is 3, right? In this case, twice Lionel's age is 2, but Maria is 3. Maria is still older than Lionel. So in this case, B would be greater than A. So these two cases show us we can break the always. We don't have an always relationship between A and B. So D is the right answer here. Okay, so that's our first test example. And this is showing us our fundamental mechanism where our task is quantitative comparison. We're comparing two quantities. We might have some upfront information. We want to find a comparison between them. And we're thinking, can I prove D? Can I break this always relationship? Let me give you guys another example here, and then we'll think about applying it to the GRE. So here's the other sample problem that the ETS has on their website. Here it is, another minute, and send me your answer when you have it. Great. Okay, so I'm seeing a range of answers coming in, and this is, I'm so glad to see that no one is picking D. Here's an example where I'm not trying to prove D, even if I'm like, oh, I don't know what these prime numbers are. These are specific values, so they're gonna have a relationship. So that's one thing to remember when we're faced with this kind of question, right? I'm comparing two quantities. Sometimes like the quantities could be all kinds of things, like the ages of Lionel and Maria could be all kinds of things. But in this case, we have specific values. I might not know how to find them, but specific values, that means actually I can eliminate D, and I just need to figure out like what are these values to find the relationship, but I've already narrowed down my chances here. So I put up here a definition of prime number. Only one in itself has factors. That's not our big focus today, is thinking about what's a prime number, but just to give us this like tiny fingernail sized glimpse of prime numbers, right? The least prime number is greater than 24. So I'm trying to get bigger than 24, but like the smallest one that's bigger than 24, like the next one that's coming up after 24. So 25, it's divisible by 5. 26, it's even, it's divisible by 2. 27, it's divisible by 9. 9, 18, 27, if we're doing our 9s times tables. And 28, divisible by 2, it's even. So 29 is our least prime number greater than 24. So 29 is going to be our specific value here. What's the greatest prime number? That's less than 28. Oh my God, I already found that 29 is quantity A. So I'm thinking of a number less than that for quantity B. I don't even need to find what quantity B is to know that it's going to be less than 29. But if I really want to do that, I can think, what's my less one? Okay, 23 is our greatest prime number, less than 28. So here's a case where A is our answer because 29 is greater than 23. Different mechanism here. We have specific values, so we're eliminating D, but we are thinking about how can I find those specific values. Okay, so this is the intro to quantitative comparison here. We always have these two quantities, A and B. Sometimes they're specific, sometimes they're not. These are our four answers. They're always going to be the same. A is greater, B is greater, A equals B. Can't determine. A, B, and C all have this implied always. Now let's think about how we apply this to the GRE. Now, as I said, I'm assuming some fundamental knowledge of geometry core rules, things like triangle area, the area of a circle, things like that. And so if you're like totally rusty on those rules, again, as I said, this will be a great one to come back to later. So the first application that I want to think about is this idea of B as a benchmark. We're going to see this in action, but what I mean by that is on a lot of these questions, quantity A is something to solve for, or it's like a bunch of words, and quantity B is a number. Whenever you see a number as quantity B and quantity A is like something else, you want to think, why are they giving me that number for quantity B? How can I use that number that they're giving me? So I'm going to give us a problem where that's what's going on. They're giving you a number for quantity B, and we'll think about how we can use it. First, I'll give you a minute and 30 seconds to think it through on your own. Here it is. I've thrown up a good rule for us to know for this question, a good hint up here in pink. So think about that as you're thinking about this question. Janelle, love the continuing to think. I'm like, I'm going to edit my own work. All right, folks. So what I want everyone to pause and try to articulate in words, and I want you to type it to everybody. So type to everyone, can I solve for quantity A, why or why not? In other words, when I solve, I mean like, can I find a specific value, like a number, for quantity A, why or why not? So type that into everybody, share your thoughts. Great. So we cannot hear. Oh, okay. So when Jean, there's great. So there's a little disagreement here. And I'm going to tell you guys that we actually can't. So a challenge here is we're like, hey, they all add up to 180, right? Now, Ekaterina noted something of like, it's not drawn to scale. Okay, really important. So what can we trust our eyes on and what can't we trust our eyes on for these? So trust our eyes that there are, that lines are lines. So I'm not like looking at this diagram being like, maybe these straight lines are wiggly lines. I'm trusting also relative position. So I'm trusting that like X is next to 70 and Y is across from X. So I'm trusting those relative positions. I'm trusting intersections or like nodes. So I'm not like, they're not going to be like actually this line goes like this all the way past it. Like if they look like they meet, they meet. What I'm not going to trust, don't trust in terms of trusting my eyes, unlabeled side lengths or unlabeled angles. So what does that mean in this case? That means that when there's this line here and y is this tucked in little shape, I am going to trust that this line is here and that y is just labeling this like tucked in extra sliver on top of this sliver. So I'm trusting that, you know, it's labeled in the right place. Maybe I'll add that here. So the labels are in the right spot. So what I'm not trusting, the labels are in the right spot, but Ekaterina is right that there's some parts we can't trust here. In this case, actually, it doesn't end up like changing the answer here, but it's good to note, like this line could actually be like here, the sort of up and down line, right? It could actually be there, or maybe like it's actually like really close to this edge. So I know that line is there. I know it's hugging along angle Y. I know it's inside the triangle, but like exactly where it is, I don't know. But that actually doesn't change our answer. So John is noting 180 minus 70 is 110. Great point, right? So our whole shape here, all the angles add up to 180. We take out that 70-degree bite that we have in the right-hand corner. That means that like this angle and this angle together equal 110. So I'm going to note that by quantity B. It's the other angles in the triangle. But x plus y aren't the other angles in the triangle. X plus y, that's my left-hand angle, but my top angle, my y, that's only that like top part of the sliver. It doesn't take up the whole shape. So even though I don't know what x is, what y is, or even what x plus y is, I know it has to be less than 110 because it has a bite taken out of it. So it has this little bite taken out at the top. So whatever it is, it can't be 110 because 110 is x, y, and this extra piece. So it's got to be less than that. So Janelle, change your mind in the right direction. B here is our right answer. So this illustrates this mechanism. Maybe I'm going to clear the slide here. So B as a benchmark. B as a benchmark means we are going to solve for the relationship to B. Solve for the relationship to B. I might not actually know what quantity A is as an exact number, but I might still be able to figure out its relationship to B. And in this case, right, it's X, Y, and then a little more would equal 110, but we don't have that little more in quantity A. So B as a benchmark, what we're going to be looking for when quantity B is a number, ask yourself, why did the GRE choose this number? They're never choosing a random number. They're giving you that number for a reason. Why did they choose this number? Are there assumptions they think I'm making? Can I use the number they gave me? That's what you want to be thinking about. Let's see another one in action. Okay, here it is. I'll give you guys another minute and 30 seconds. Awesome. Okay, thanks for sending our answers. So one thing, right? Someone asked, can we assume this is a 30, 60, 90 triangle? Always be wary of assumptions, right? I'm going to trust that the labels are right in the right spot. I'm going to trust that straight lines are straight, that they're intersecting where they're intersecting, but I'm not going to be like, oh, this must be the certain kind of triangle, right? I want to like what they give is a hint. And also what they don't give is a hint. Okay, so I'm going to ask you guys, I'll tell you guys that A is the right answer, and I'll say why in a minute, but a lot of you guys got this one. A is the right answer. Why did they give us 90 as quantity B? Type into the chat. Why did they give us 90 for quantity B? How can you use 90? Type it to everyone. Okay, love it, right? So part of it is tricky, right? X looks like it's 90. We might think must be C. X looks like 90 degrees. And so they're giving it to so that we can use it. So Dhruvi says, so you can prove with the Pythagorean theorem, right? So we can use that 90. So one way we can use B as a benchmark is to cheat. I'm going to call it cheat with B. In other words, plug in B. So sometimes when B is a number, we're going to cheat with it. We're going to plug it in. So let's say I plugged in 90. In that case, we could use the Pythagorean to solve for all of our sides and check that it works, right? If it's 90 and our two other side lengths are 6 and 8, our two legs are 6 and 8, plugging into a squared plus b squared equals c squared, then our hypotenuse would be 10. But wait, our hypotenuse here is 10.5, right? So it can't be 90 because if it were 90, our lengths would actually be different. We can use that Pythagorean theorem to test like, do these lengths match up given our a squared plus b squared equals 6 squared, right? Like as Almoga is saying, right, to pick option C, 6, 8, and 10 are triplets. They go together in a right triangle, but we have 10.5. We don't have 10. So is it going to be bigger than 90 or smaller than 90? It's going to be bigger than 90 because our angle size corresponds to its opposite side length. So the bigger the angle, the bigger the side length that's opposite it. The smaller the angle, the smaller the side length that's opposite. So we can kind of picture that, right? Like if X were smaller, that 10.5 length would be smaller, right? But since 10.5 is longer than 10, that means we've opened up our triangle even more to fit 10 in. Like we went from having that 90-degree angle, then we opened up a teensy bit more to get that extra like 0.5 length in there. So that means whatever X is, it has to be greater than 90. So again, with this idea of cheating off B, when quantity B is a number, you're asking, why did they use this number? Are there assumptions? Can I use it that they gave me? And one way we can use it is to plug it in. We can like imagine, what if it were C? What if they were equal, right? And see what happens. Okay, I'm going to give you guys one more example with B as a benchmark, and then we're going to see some other examples here. Okay, another minute. Go for it. I'm going to say a verbal hint, which is that it's not D. Lots of you guys are sending me D as an answer. D is not the answer here. Okay, so again, I'm thinking, right, they gave me a value for B. When quantity B is a number, I'm asking, why did they choose this number? Are they assumptions that they think I'm making? Can I use the number they gave me? Can I use by plugging in? So maybe I'll think, well, what if the area were 9 pi? If the area were 9 pi, if the area were 9 pi, and our area, I put our formula up in the top right, is pi times the radius squared. That would mean our radius would be 3. And if our radius is 3, and maybe I'll put this to the side. So I'll find that by saying like pi r squared equals 9 pi. Our pi's can cancel out. We've got it on both sides. So r squared, our radius squared equals 9. So our radius equals 3 in that case. And then our diameter, which is 2 times the radius, would be 6. But if I look above, AB, which is 6, is not the diameter of the circle. So it will not C. It is not C, right? If I cheated off B, if I cheated by plugging it in and said, okay, what if the area were 9 pi? We found that the diameter was 6. We know 6 is not the diameter. Type into the chat, how do we know? So we know it's not equal. It's not equal. How do we know if A or B is greater? Type into the chat to everybody, right? The area can't be 9 pi, but how do we know if A or B is greater? Type it into everybody. Very good. Okay, so you guys nailed it here, right? Our diameter is our biggest length in the circle. It's our biggest length. I'm just going to move this up here. Diameter is our longest length. So whatever diameter is, it's going to be longer than 6. That means our radius is going to be bigger than 3. So whatever it is, it's bigger than 3. So our final area is going to be something bigger than 3 squared times pi. So our final area will be bigger, and A is the right answer. Okay, so these are illustrations of B as a benchmark as it applies to quantitative comparison questions. We're going to see another strategy in a moment, but let me pause here just for a second. So I'll stop sharing for a moment. Any questions, and go ahead, just type into the chat, any questions about this idea of B as a benchmark as it relates to geometry? Okay, not seeing any questions yet, but if you have one, like type it into the chat and I will answer it. Let me keep going. We're going to see some other strategies in play. Okay, so next I want to think about proving D and geometry. And to begin, what does it mean to prove D in the context of quantitative comparisons? So think back to that Lionel and Maria question that we saw earlier. Proving D essentially means testing cases or finding examples to break the always between A, B, and C. So we've proven D when we've shown there isn't that always relationship. What does that mean for geometry? What that means, it goes back to when Ekaterina was like, we can't trust the diagram entirely. It means being skeptical of the diagram and thinking about whether we can stretch and squish the shape. And in particular, we're going to look for unnamed lengths and unnamed angles. So for example, if they were like, compare this pink line and this green line here, but they don't tell you anything about it. It might be like the green one looks longer, but they haven't labeled the lengths or the angles. So I'm actually going to be skeptical of that. So I'm being skeptical of unnamed lengths, skeptical of unnamed angles, and thinking whether I can stretch and squish the shape to actually vary it and show that sometimes our relationship, we can break that always. Sometimes A is greater, or sometimes B is greater, or sometimes they're equal. So here is an example, and this one is also from the ETS website. I'll give you guys 1 minute for this one, and then we'll see another example. Go for it. Okay, great. D is our right answer here. This is one of their example questions, right? It looks like they're equal. PS and SR look kind of equal, but hey, maybe that line actually is here, you know, in which case SR is pretty short and PS is pretty long. Or maybe the line is actually, you know, all the way over here, in which case the reverse is true. You know, maybe PS is pretty short and SR is really long. So we can stretch this shape, move that line around because it's not actually labeled. Like we don't know if it's exactly equal to prove D. So again, it's like a visual proving D of showing sometimes A is greater and sometimes B is greater. So D is correct here. Let's see another example of thinking about what do we know and what don't we know. Here is another example. All right, tricky question here. I'm seeing lots of like question marks. Janelle is like, you told us stretch and squish, but they told us the dimensions. How, like, what am I supposed to do with this, right? So let me ask a question to you guys. And again, type it into the chat. What do we know and what don't we know about these figures? So what do we know and what don't we know? Type it into the chat. Janelle, careful though. Oh, sorry, that wasn't to everybody. Everybody do great. Sorry. Keep it coming. Okay, so we know the side lengths. Good. Okay, we know side lengths. We know so the opposite sides have the same measurement. So I can add that in, right? So if that side is 10, that side is 10, this side is 6, this side is 6, right? So I can add in these other side lengths. Good. Okay, so maybe part of this. Here's what I want. Good. Okay, so Lauren says they don't give angles. So this might also come to this idea of parallelogram and defining that. Parallelogram, it's not necessarily right angles, right? This doesn't say rectangles, it says parallelogram. So a parallelogram could look like, could look like this. So our key here, and I'll spoiler alert, D is the answer, but I want to get to Y. Right? So don't tune out because you know D is the answer. I want to get to why. The reason D is the answer is because we don't have angles. So it's very key. We want to be skeptical, spelling that wrong. Okay, skeptical because no angles. So let's picture another, way that these could look. They might look like rectangles. They might be rectangles, right? They look 90, they're not necessarily, right? It appears to be a parallelogram or it appears to be a rectangle, but especially for quantitative comparison, we want to be like, wait, but what aren't you telling me? Can I prove D? And for geometry, that means can I stretch and squish? So maybe my parallelogram WXYZ really looks like this. Maybe our angles are quite tilted to the side. Maybe our ABCD is straight up and down and our WXY is tilted to the side, or maybe vice versa. Now you might be saying, but like the sides of WXYZ are so much bigger, wouldn't it still be bigger? And I want you, maybe I'll start sharing in a second. I'm just going to stop sharing for a second. So just look at me and think about, I wish I had a box right here in the room, but like picture, maybe you have a box in your room, a cardboard box that you got from a delivery and you're getting it ready for recycling. It goes from being a nice full cardboard box that has your fun items in it. Then when you flatten it, the sides are still the same. You didn't somehow shrink the length of cardboard you gave, but when you flatten that box, it goes down to almost no area, right? Like you flatten it down almost to a piece of paper that you can like slip into your recycling bin. It goes to almost zero area when you flatten that shape down. So maybe, I can't see you guys, you're not on camera, but do it with me. Stretch out your arms. This is like great like energy too, because we've been sitting, right? So a moment of stretching, stretch out your arms. You're not changing the length of your arms. Now make them into like a really big shape, like a circle, right? Like, oh, so even and regular, but then I can like fold my arms together to make like a really thin shape that almost like has no area in it. And the reason is I'm like flattening the box. I went from being a nice regular upright shape to flattening the box and being almost zero as a shape. So let's see this in context. Let's go back here. Actually, before I go back, I'm going to tell you guys a rule. And I'm going to type it, I'm going to put it onto a whiteboard. So here, let me write it onto the whiteboard. Thinking about maximizing and minimizing area. This is what stretching and squishing means. Maximizing and minimizing area. We are going to maximize area by making the side lengths and the angles more even and regular. So that means If all my angles are even in this parallelogram, they're all going to be 90. We're nice and upright. It's like everything is more upright and symmetrical, right? We're going to get a nice bigger shape. It's like when you puff out that box, when you like unfold it again, we've actually made the angles more even. We minimize the area by flattening. That means one angle gets really small and one gets really big. One angle gets tiny, like so tiny that it's almost like 0 degrees, right? One angle gets big, and we can minimize any shape. We can minimize almost down to 0, or any parallelogram. We can minimize, I shouldn't say any shape, right? Like a circle, I can't flatten to be 0, but like we can minimize a parallelogram to be almost down to 0, thinking about flattening that box here. So let's see this back on our problem. Maybe B is greater than A. Maybe they're both nice upright rectangles and our side lengths on our WXYZ are bigger. That means a bigger area. But maybe our WXYZ is a flattened box and it's really like scrunched all the way down, like almost like all the way down, like to a nice, I'm drawing kind of funkily, right? But we're squishing those long sides all the way down, making it smaller than ABCD, which is maybe more upright. Okay, tricky question. I have one more question theme to show you guys, but before we do that, I'm going to pause again and ask you, what questions do you have about this question and or about this idea of proving D in geometry, which again means in this context, this idea of like, can I stretch and squish the shape? And I'm looking especially for unlabeled angles and unlabeled side lengths to be like, how could I actually change it? So what questions do you guys have here? Awesome. Okay, so Caroline was like, can you say again, what can we trust and what can't we trust our eyes? This is so important for the GRE geometry. So I'm going to reiterate that. I'm really glad you asked that. So we can trust that labels are accurate. We can trust that straight looking lines are straight. We can trust relative position. In other words, like 3 is next to 4, you know, we can trust the relative. Oh, I'm glad that the stretching was helpful. We can trust the relative positions. We can trust like that things that seem to meet are meeting, right? We can trust intersections or like meeting lines. Here's what we are going to not trust, and it's very specific. We're not going to trust unlabeled lengths. They actually, if they're not labeled, they could be long or short. And we're not going to trust unlabeled angles. Oops, I spelled lengths wrong. Unlabeled angles, which like could be a tiny sliver or a huge bite. We can be skeptical here. Now this can feel like, Jerry, why are you even giving me these diagrams? And this, you know, if you're not going to be accurate here. And this goes to almost like the meaning, or like I shouldn't say the meaning, but like this question type quantitative comparison is all about thinking like a lawyer of like, well, what exactly did you tell me and what didn't you tell me? What you didn't tell me, I'm going to take that to court, right? So you didn't tell me that these were right angles. So I'm not going to take your word for it, right? And what does that mean if they're not right angles? Like, what are the ramifications of that? So it's like I'm reading a contract. I'm like, well, what exactly did you promise? And what didn't you promise? So I didn't know that there were right angles here, so I'm going to be very skeptical. Okay, when Gina asks, how do you start seeing math in a more visual way? That's such a deep, profound question. I don't know that I have a really good concrete answer to that. I'm sorry, Wendy. I think geometry is like a really good place to start. I feel like geometry kind of lends itself to it, but okay, I want to show one last theme here. And for this, I'm not going to tell you what the theme is in advance. I'm just going to show you 3 questions, and I want you to see if you can figure out what the theme is. So for these 3 questions, I'm going to give you, let's say 5 or 6 minutes. And what I want you to type to me is, what do you think the theme is? And I put a hint already in the top corner that the area of the triangle is base times height. Okay, take a minute or take a couple minutes. Oh no, Philip. That wasn't what I was thinking. I'm sorry. Yeah, and I'll highlight it up here. It's 1/2 times the base times the height. And a key I'm going to say is that like base and height are not the same as the lengths, as like the side lengths. The height is the line that drops at a perpendicular angle from the ceiling of the shape to the floor. So for example, here's a triangle. Well, let me give a different example actually. Let's say like, here's a triangle. If this is the base, the height isn't this line. The height is going to be like a line that we drop at a perpendicular, in other words, 90-degree angle that goes from like the peak of the ceiling or like the top of the roof down to the floor. So that's our height. Okay, so don't type keep typing your questions in, but actually you guys have like 3 or 4 more minutes to work on this. So keep working on them, try all the problems, try all 3 problems, see if you can come to an answer, and then try to reverse engineer the theme from that. So actually just try to do the problems. Yeah, sorry, Janelle, I didn't clarify that. Do the problems. Okay, Janelle helpfully pointed out that I was missing the 1/2 on the top corner of my slide there. I'm so sorry. It doesn't change the answers, but it should have been base times height times 1/2. My apologies. All right, guys, I'm going to give you guys a couple more seconds thinking about these, and I'm just going to walk through them. If it's feeling like overwhelming, you have no clue what I'm getting at with the theme, no worries. I'm going to walk through the solutions to these. All right, let's discuss these. Harold asks, will we be given a calculator for the GRE? And indeed you will. So you do have a calculator on the GRE. Also, some of these questions, right, you might like from today or from other parts of your studying, you might be like, wow, I learned from this that like this kind of question is super confusing to me. That's great information to have. You can either be like, okay, I'm going to dedicate some time to like trying to master this. Or you could be like, you know what, I'm going to strategically decide not to focus on this thing that's feeling really confusing and know that I'm going to guess and move on this kind of question and save time for some future questions. Now, these questions here, I'd say like, the diagrams are, you're like, blah, what's even going on? I think that if we peel away some of the layers of the onion, they're more like more bark than bite is one way I can think about it. The theme here is that they are all equal and they are all secretly equal in a way that I want to get to that's specific to questions that test triangles. So C is our right answer to all of these. All of these are figures that are equal and they're equal in a patterned way that I hope that you can notice in the future. So let's look at our first one here. So notice parallelogram KLMN. Let me spotlight that here. So KLMN, this one here, and the JKLM, this one here. So this one here, they share this bottom triangle. Yes, Wenjin, right? Base and height are going to be equivalent on all of these. That's what it gets to. So they share this bottom part here. So actually, I'm just going to be like, whoop, forget about that bottom part. They share it. That means what I really want to compare here, like I don't care about this bottom situation, right? That part's equal. I want to know if I'm comparing quantity A and quantity B, is this shape, is JMK bigger than MNK, you know, versus this shape, right? Is this triangle here? Maybe I'll highlight it in a color. I'll be like, is this pink triangle here bigger than the triangle behind it? So, right, triangle is 1/2 base times height. So triangle is 1/2 times base times height. Whoa, I'm looking again and I'm like, oh my God, they have the same base. So I'm like, now I'm not even comparing these triangles. I'm just like, which height is bigger? And I'm looking at the height. Okay, so N, I'm going up my axis here. The height is 5. J, oh my goodness, the height is also 5. Our y-axis is also 5. So their height is also 5. So secretly equal. So what I'm looking for, it's this very complicated looking diagram. But if I start to peel away the layers of the onion, what I'm looking for, secretly shared bases, secretly shared heights, secretly shared triangles, right? They're hiding that. Really, it's comparing these triangles, but I'm looking for triangles and I'm looking for secretly. By secretly, I mean it's obscured in a more complicated looking diagram, shared bases and shared heights that might be rotated, right? I might not be seeing it immediately, but if I pare it down to like, okay, I'm looking for the base, I'm looking for the height, I can start to spot that. So I'm really looking for base and height. So again, WXY and WZX, maybe again, I'll make one of them pink, right? So I've got my pink triangle and the one behind it, WX, we've got that shared base. So again, we have a shared base. And I'm like, okay, the height. Now, Rina told me, be skeptical of my eyes. You know, what if actually this line is at a tilt? You know, and these two heights here, if I'm drawing it in, what if these two heights, I'm drawing in our height, it goes like from here, that's one height. And then from here is the other height, right? It's like dropping from the top of the shape, like the highest part of the shape, all the way down to the floor. What if they're not equal? But they tell us A, C, and B, D are parallel. That means our two heights here, again, are parallel. So we have these secretly shared bases and secretly shared heights. So again, I'm looking for triangles, and then I'm trying to peel away and think, well, what's the base? What's the height? Are they actually shared here? In this last one here, we have a rotated triangle. So the product of BE and AC, okay, well, in this case, that's the base of this triangle could be AC and the height is BE. But what about here, BC and AD? Well, if I flip it on the side, then my base is BC and AD is the height. And wait, it's the same triangle. So our product is going to be the same because our area of one triangle is always going to be its own area. So it is going to be the same number because 1/2 times this base and this height is going to be the same as if I like called the base and height something else because I flipped the triangle over, but it's still the same triangle. So secretly equal, we're looking for triangles. We're looking for shared bases when they're actually like sharing a line and shared heights. Okay, we are almost at the top of the hour, so I'm going to stop here. That is actually the end of the time. I'm just going to tell you guys, just to summarize, B as a benchmark is what one of the things we talked about. That's when B is a number and we're thinking like, why did they give us that number? How can I use it? Prove D on quantitative comparisons, looking for unlabeled angles, unlabeled side lengths, and secretly equal, looking especially for triangles. We have some upcoming classes. Check them out online. Also, all of our free webinars are recorded. Check out our YouTube channel. It has all of the free prep hours of the past. So between all of those, you have a lot of great information. There's 2 more minutes. So if anyone wants to stick around and ask like one question, go ahead and do so. But otherwise, have a great rest of your night. And so great to meet you all. Thank you so much, and hope you enjoy the rest, and good luck with the rest of your studies. And thank you guys for the kind remarks. Very sweet. All right, I'm going to go ahead and close the Zoom. Thanks again to everybody, and enjoy the rest of your evening. Bye-bye.